Hi guys, in this video we're going to be doing a large sample hypothesis test comparing two proportions. Now it's important to point out that the two proportions are coming from two independent samples. Okay, so let's get to this very generic example I've set up here. First off, I have group 1 and group 2 here. Group 1 represents our first population and group 2 our second population. So what we do here in these two sample tests is we take a sample from group 1, and that's what N1 is. So this 1 is a subscript indicating that that's the sample taken from group 1 or population 1. Okay? So we took a random sample of 535 observations. Of those 535, 115 met this condition that we're interested in, what we'll call success, okay, whatever it might be. So you can imagine this variable as a binary variable, something like a yes or no. So 115 were yeses. That was the thing we were interested in of the 535, okay? And likewise with group 2, we had a sample size of 596. We took an independent sample here, and meaning independent from the first. And of those, 116 were successes. So I calculate the proportions. So this is p hat 2. P hat, if you recall, is the sample proportion. And I give it a little subscript so I know it comes from population or group 2. All right, and you'll see that also I have p hat 2. So how did I calculate these quickly? I just used Excel as a calculator, did B4 divided by B3, right? Simple calculation. Now we get to the question of interest. Is there sufficient evidence to conclude that the proportion of subjects with the condition of interest differs from group 1 to group 2? In other words, is the sample proportion from group 1 different than the sample proportion from group 2? Okay, and so this is ripe for a hypothesis test, right? So it says test the appropriate hypotheses using a level of significance of 5%, right? I'm reading that right from here, all right? So we want to set up our null hypothesis. First off, in these two sample hypothesis tests for proportions, we start out by assuming that the population proportion from the first population equals the population proportion from the second population. Okay, that's just a great place to start with our null hypothesis. So as you can see here, I kind of rewrote that slightly differently. I just subtracted both sides by P2, and I ended up with P1 minus P2 equals 0. So that's saying exactly the same thing as this. This version just gives us a little bit more versatility in the future if we want to do more advanced hypothesis testing. Okay? Now the alternative hypothesis, now whether your text writes that as H1 or HA, is that P1 differs. We want to test if it differs. That's straight from the question here, right? So this is, we have to use this symbol here, differs from P2, okay? And once again, you do a little algebra and you can rewrite this as I've done over here, okay? So this is our hypothesis test statements, very clearly written with the appropriate level of significance, right? So we're set up and ready to kind of start the calculations and get to our conclusion on whether we reject or fail to reject HO. All right. First thing we need to check is, as I said in the very beginning of this video, this is technique we're going to use here is for large samples only, and I put that kind of I'd like to put that in quotes because that means different things in different scenarios. Okay, so large sample approximation is something we do a lot in statistics. All right, in this specific condition, the the thing we need to test to see whether this qualifies for a large sample approximation so that we can use the techniques we're about to unfold is to check whether n times p is greater than or equal to 10. So some textbooks will have a slightly different number than 10, all right? So text I teach out of uses 10, some use 5, okay? What this means is that your sample has at least 10 successes and n times 1 minus p is greater than or equal to 10, and 10 failures. So what this is saying is, does your sample have at least 10 successes and 10 failures? If so, you can continue to use this large sample approximation. All right? Now we got a bit of a problem. We don't know exactly what p to use here yet to test this, right? We seem to have this guy here and this guy here, but not quite clear which one to use. So now's where we get a little bit into we have to calculate a few things before we can check this, but this is the general idea. Excuse me. Now, notice the null hypothesis says that P1 equals P2, right? That's where we're starting from. That's the null hypothesis is what we initially assume to be true, no matter what hypothesis tests you're doing, okay? So the null says that P1 equals P2, then we know that P1 equals P2, but we don't know what P1 and P2 equal to, right? The null says that they're the same value, so not really necessary for us to even have a subscript. So basically we know that there's a common P, right, between P1 and P2, but we have no idea what it is. P1 equals P2, but they could equal 0.01 or they could equal 0.99999 or anything in between, correct? So we need to come up with some estimate of what that common proportion is, because we're going to need that in a lot of our calculations. For example, for our test statistic. All right, so we need to come up with this an approximation for what P1 equals P2 equals what. Okay, so we will calculate something oftentimes called the p hat combined. Okay, sometimes you might even think of this as the common. Okay, so this is the p hat combined, and what this will attempt to do is to combine the two p hats that we have, giving slightly more weight to the p hat that came from the bigger population. So this one would get slightly more weight here. Slightly more weight because it came from a slightly larger sample size. But the point is to combine these two p hats, because if the null hypothesis is true, which is what we start out by assuming in the hypothesis test, then what we're saying is that both these populations have the same proportion of successes. So both of these p hats that we're looking at here are estimates of that common p, right? So why not combine these two estimates into one stronger estimate, so to speak? And that's what this guy is, p hat combined. Okay, and so how do you calculate this? It's quite easy. You take the first sample size, multiply it by the first sample proportion plus the second sample size times the second sample proportion, and then divide that by the sum of the sample sizes. Okay, and that will give you p hat combined. And hopefully I gave enough motivation of why we could use such a measure. Okay, and you'll see how we're going to end up using this a lot for the rest of the hypothesis test. And that's basically what I've calculated here. Okay, so let me get rid of this writing and just show you the formula I have here. So what I've done here is I have done n1 times p hat 1 plus n2 times p hat 2 divided by n1 plus n2. And I've done it all in Excel using cell references. Alright? And you'll see we get a p hat combined of 0.204. So this is an estimate of what P1 and P2 equal to. Okay? So we're going to use this value to first check this large sample condition. So checking that large sample condition, we see that we have both N1 and N2 having large samples. So if you like, we have 4 things to check. So we can check these. So N1 times P hat C, clearly greater than 10. N1 times 1 minus P hat C, clearly greater than equal to 10 failures. Now we need to do the same thing for the second sample. So N2 times P hat 2. And finally N2 times 1 minus P hat C. And clearly you see that both of our samples have at least 10 successes and 10 failures, right? Or in other words, they're greater than or equal to 10, all 4 measures. So we can give this a check. We have our large sample condition clearly satisfied. We can actually go through with calculating our test statistic, which is going to be a Z test statistic. So I'll give you the formula for now, how to calculate the test statistic for this hypothesis test. So this is a little long. So first you do p hat 1 minus p hat 2 in the numerator, minus, and let's put this in parentheses to be clear, minus p1 minus p2. So notice without the hats, these are population proportions. With the hats, they're sample proportions, divided by the square root of p hat c times 1 minus p hat c divided by n1 plus, again, p hat c times 1 minus p hat c over n2. Now this whole denominator is under the square root, by the way, so be careful. Okay? So we need to calculate this test statistic. You'll notice from our null hypothesis that P1 minus P2 is 0. So this is just going to be 0. Okay, so that'll simplify things a bit. But you still have values here that you need to plug in, namely from here and here. Okay? And if you've written this formula down, I can erase this now. So that's our test statistic. I've calculated that here using Excel as my fancy calculator. You see I've done B5 minus B10. So I've done P hat 1 minus P hat 2 over the square root, and be very careful with your parentheses, alright, if you're using Excel. To do this properly, you need to make sure you put the parentheses around fractions and around the entire square root. Okay, so if you do this carefully, you should end up, with these numbers, you should end up with a z-score, a value of 0.846407. All right. So far we've used Excel as nothing more than a calculator. All right. Now, as you know, with a test statistic, to make that final decision, we can get a p-value, compare that p-value to alpha, and see whether we reject the null hypothesis or fail to reject the null hypothesis. Okay? Remember, in hypothesis testing, you start out by assuming that the null hypothesis is true, and not until the very end of the test, when you make your decision to reject HO or fail to reject HO, do you let go of that null hypothesis. So let's see what happens, and then we'll talk about the conclusion. So we need to calculate a p-value. Especially with a z-test statistic, you can even calculate a p-value by hand if you have a z-table, standard normal table. But since we have Excel, I want to teach you how to do this using one of the functions Excel has built in. So here you see it's a two-tailed test first off, because of my alternative hypothesis is not interested in any specific direction, right? It's interested in different. So different, that came from here. Different means different this way or different that way, okay? Whereas these guys are one-tailed alternatives. They mean different in a specific direction, right? So here, whatever we're doing to two tails. So that's where the times, we start out by doing 2 times, okay? Then we're doing 1 minus, and this is the function, norm.s.dist, okay? The first argument is your test statistic. The second argument is you put true in for cumulative, okay? And then you do 1 minus that in parentheses, and then you multiply that by 2. Okay? I'm going to go out of this, show you visually what this means. We're looking at the z distribution here. Centered at 0, correct? So this is the z distribution. Our test statistic is 0.846. Okay? The definition of a p-value is the probability of getting a test statistic as extreme or more extreme than the one that we got, given HO is true. Now, extreme is a more general word than bigger or smaller. It means different things. It can mean different things in different hypothesis tests. Depending on that alternative hypothesis, the definition of what extreme means becomes clear. So, in the two-tailed alternative hypothesis, extreme means in both directions extreme. Okay, so first let's start by getting extreme in this direction. Extreme means that way. Any value as extreme or more extreme than the one that we got, which was this from here, would be deemed, anything out here would be deemed more extreme than what we got, right? But because our alternative is interested in any direction of any direction of extremity, in other words, because we were only testing it different, we should also check different in the other direction. So we do negative of our test statistic, and we get the probability of getting anything extreme, more extreme in the other way as well. And so this, as you know, and this area are equal. They're mirror images of each other. These two shaded areas represent our p-values. Anything out here would be more extreme than our test statistic. Okay? So what we do is we get the probability of getting one of these areas, and then we multiply that by 2. Now the formula that will get me this number here is 1 minus norm.s.dist. And then I put in my test statistic, and then I say true. Okay? Because this is a positive test statistic, I have to do this 1 minus. Okay? If it was negative, I would just do norm.dist. Alright? This takes a little understanding of the cumulative distribution, which we don't have time to fully go into here. Okay? But take this as a rule for using this function in Excel. If you have a positive test statistic, you do 1 minus norm.s.dist. If you have a negative, you don't need to do the 1 minus. And if you have a two-tail test, then further you need to multiply what this value is by 2. If it was one tail, you don't need to multiply this by 2. Okay? But in this case, we have a positive test statistic, so I have to do 1 minus this function. Z is just this value. Right? And then, because it's two-tail, I need to multiply this by 2. And if I do that, as you can see here, 2 times 1 minus norm.s.dist, B14 is the Z test statistic that we calculated together, and comma true, close those parentheses, we get a p-value of 39.73%. So the probability of getting a test statistic as extreme or more extreme than the one that we got, given HO is true, is quite likely. So in this case, we are probably not going to reject HO. And in fact, if we compare to alpha of 0.05, we see that this is definitely greater than 0.05. So let's just write that right here. So that is, if you just remember it by the rules, if your p-value is greater than alpha, you fail to reject the null hypothesis. So our conclusion is that there is not sufficient evidence to conclude that the proportion of subjects with the condition of interest differs from group 1 to group 2. In other words, P1 equals P2. These two groups, we have not shown convincing evidence that their proportion of success for whatever this is that we're measuring on both these groups is different. Okay? Remember in hypothesis testing that when you fail to reject, that's not as powerful of a conclusion than when you reject. When you reject, you're showing evidence against the null hypothesis and for the alternative. When you fail to reject, you're simply saying there was a lack of strong evidence against the null hypothesis. So you fail to reject. It's a slightly weaker conclusion. Okay? So I hope this was helpful. This is a 2-sample hypothesis test. This was a little bit over your head, but you got through to this point, and you might want to go back to check out the 1-sample versions of these tests and then come back and check the 2 samples. Okay? So, again, hope this was helpful. Make sure to comment, favorite, and share. Till next time, have a great day.